This is part 3 of section 11.4. You select a family with 3 children if M represents a male child and F represents a female child. The set of equally likely outcomes for the children's genders is as follows. It's every combination of male and female with 3 of them, okay? Find the probability of selecting a family with. Now, one thing I do need to say here is, once again, as far as this book goes, which means as far as your homework on the computer goes, there's male and female and there's nothing else. So just keep that in mind. Also, of course, your book doesn't use sex and gender properly either, but, you know, we deal with what we need to. Okay, so let's figure out these probabilities of exactly one male child. Okay, well, how many different possibilities are there? 5, 6, 7, 8 different possibilities. Okay, and how many of these have only one male? That one does, that's 1, 2, 3. 3 of these. So that probability is 3/8. 3/8 does not reduce, so that is your answer. Okay. So what is the probability of at least 2 females? Again, there are 8 possibilities, and I just need to count how many of these have 2 females or 3. So 1, 2, 3, 4. So that probability is 4/8. Which reduces to 1/2. Okay, so that's theoretical probability, where we are able to list everything possible, and basically we know everything about what this experiment can be and what it can't be. Okay, now we're going to talk about empirical probability. This applies to situations in which we observe how frequently an event occurs. So imagine that we're doing an experiment to see, and we're recording when we flip a coin, how many times we get heads, how many times we get tails, okay? Or just anything where we have a bunch of data, but we don't know in general, okay? This all should be clear once we get to an example. And then we have what we call the law of large numbers that says an experiment is repeated as it is repeated more and more times. The empirical probability of an event tends to get closer to the theoretical probability of the event. And yes, I see a typo there. I will fix that. Okay, so how do you compute the empirical probability? The observed number of times E occurs. This is basically the same idea. It's how many times can that event occur? Or how many times have we observed that that event occurred over the total number of observed occurrences. Okay. So let's talk about this. Consider the following experiment where we flip a fair coin and record the number of tosses that lands on heads. We know that the theoretical probability of landing on heads is 1/2 or 0.5. So let's just look at this data that we have. So let's say we flipped it 10 times. We got heads 4. That would mean that the empirical probability after this many experiments, we got 4 heads out of 10 tosses. So that's 0.4. We keep going. After 50 tosses, we had 27. So 0.54. After 100, we had 44. After 1,000, 530. After 10,000, see what's happening here? Okay. As these numbers, it bounces around a little bit in the beginning with smaller numbers. It usually is going to bounce back and forth around the true probability. But as the numbers get larger and larger and larger, then this value should get closer and closer and closer to 0.5. And you can see that it does that. It bounces around a little bit, but the more times you do the experiment, the closer it should be getting to the actual theoretical probability. So let's work a few examples here. So we're given this example problem where we're given this chart is the number of people in the United States living alone in millions. Okay, and we are asked to calculate the probability expressed as a decimal rounded to the nearest hundredth, so that's 2 decimal places, that a randomly selected American living alone is male. Okay, so the probability of male would be, so how many total people are we talking about in this universe? Well, 29.3. So 29.3 is going to go in the bottom because that's the total number of quote unquote experiments, the total number of people we're talking about. Now, how many males were in this? Well, here they gave you the total males, so that's 12.5. So if we do this calculation, you get 12.5 divided by 29.3, and you get approximately 0.43. So the probability that a male is living alone is 0.43. Now, let's find the probability that the person is female. Okay, so this is going to be, again, over 29.3. Okay, and how many different females? 16.8. Do this calculation. And you get about 0.57. Okay, notice one thing. Like I said, this book considers males and females and nothing else. So if you're talking about the number of people, all the people who were being questioned here, then they were either male or female. So this should take care of everyone. And if you look here and here, if you add these two numbers together, you get 1. So that makes sense. Now, I do want to say that because we rounded, you could add these together and you might get slightly more than 1 or slightly less than 1 just because of the rounding error. But keeping that in mind, that when you're dealing with something that should take care of everything in the sample space, then the probability should add to 1.